All right. Let's see.
All right.
All right. Thank you, Randy, for the introduction, and good morning, everyone. Thank you for joining today. Let me get my presentation started here. So yeah, I'm a machine learning scientist at NCAR and currently head of our relatively new analytics and integrative machine learning group. One of our kind of missions we have as part of this group is working across NCAR, the university community, the Weather Service, all kinds of different organizations to figure out how best to integrate machine learning systems into various workflows, whether they be a researcher's a science workflow or in this case, an operational weather forecasting workflow. Because there's a lot of challenges along the way that it's a lot more than just training the machine learning model and letting it go. There's a lot of infrastructure and other choices that have to be made along the way in order to make a successful machine learning system. So why I'm here, been spending quite a few years since my undergrad working on machine learning and different kinds of weather forecasting challenges. And it's tempting to come into the process just thinking that the end users just need, as this comic illustrates, that we think of the end users maybe just needing our algorithms to dig into their complex data and unearth the patterns that lie within. But often a lot of the needs are more practical, whether it's just in this more comical case about just not being able to even access your equipment.
John,
Yes.
we're not seeing your presentation. We're seeing the not the presentation. We see you in with the slides on the left.
Okay, let me see if I can fix that. Thank you for the heads up.
Yep, there we go.
Is that better? Okay.
Yep, perfect.
So this kind of XKCD comic sort of illustrates this problem where initially coming in, you think just the algorithms will solve everything, but really we need, as a machine learning practitioner, I want to be able to communicate with you as the SUs and forecasters about what your actual needs are in terms of machine learning systems. Where do you feel like the gaps in your current forecasting process are? And are they things that we could actually solve with machine learning, or maybe there are actually other issues that need to be solved first before machine learning, or maybe machine learning doesn't make sense at all for your particular use cases. But I wanted to kind of show what machine learning can do, and let's see, here we go. Kind of talk about the whole pipeline, how you build machine learning systems, and then some of the existing challenges from my perspective about trying to move machine learning into an operational context, and maybe some potential solutions and ways forward on that. What's kind of pushing this is that we, like as shown in this figure on the right, machine learning has kind of exploded in popularity in meteorology, and there's a lot of tools now that so a lot of people can sort of enter the machine learning domain and start building their own systems. But going from that initial experimentation to a full operational product requires overcoming a lot more hurdles. So we'll talk about some of these along the way. First, I want to provide a kind of nomenclature of the different terms that get floated around within machine learning and deep learning and AI. So I define AI or artificial intelligence as just a kind of catch-all term for methods for computer systems to perform human tasks. And I like to think of AI as like kind of the whole system that's involved with machine learning as a key component of that system. With a lot of classic AI systems, they were built as what are called expert systems, where you ask an expert, like a forecaster, how do you make a weather forecast? What are the things you look at? What are the kind of internal rules of thumb in your head? And then you try to write a computer program that mimics those rules. Turns out it's a lot more complex than just asking someone how they do things and then writing a program to mimic that. And it's a lot easier to do what's called machine learning, where you provide a lot of examples of some kind of set of inputs, whether it be some kind of weather map or weather data, and then some outcome, which would be the forecast itself, or what actually happened in real life. And then you optimize your computer system by looking at these examples over and over again, and really making its predictions better until you get to a certain level of accuracy that is desirable. Traditional machine learning works really well with things like tabular data, but if you want to use more image-like data, you need something called deep learning, which is a subset of machine learning that features neural networks with multiple specialized layers for encoding space and time information. And we'll talk more about what's involved with that later in the presentation. The machine learning pipeline is more than just the machine learning model training itself. There's a lot of work that has to be done to the data that feeds the machine learning model before we can even get to the models themselves. We often need to define our problem, gather data, prepare it. This is actually about 70% of the data, the machine learning kind of practitioner workflow time process. And the rest is taken up with the model training and evaluation and interpretation. And when you get a successful system built through this whole pipeline, there's a whole other funnel of deployment operations that one has to go through to make this an actual product that is used on a daily basis and is helping decision makers save lives and property. So the first, what are the ingredients for machine learning? Now we have kind of this broader pipeline in mind. The first component that is really the key to all this is a well-defined problem. Often a lot of problems are kind of more vaguely defined, and that's where one can run into trouble later on if you don't specify kind of what are the conditions for success, what is kind of the actual goal of this. If you don't do that first, it's easy to get lost in the weeds of choosing different algorithms and like messing with parameters and all those kind of things, and then you get bogged down in that and never actually build your whole system. You also want to know like what data are actually available for this problem. Machine learning requires a fair bit of data. If you don't have a fair bit of data for this problem, then you shouldn't try machine learning on it. You should also know what your constraints are in terms of like time constraints, space constraints, computational constraints. How is the performance judged? What is your criteria for success? Do you have a certain level of accuracy you need to meet? Are there other physical criteria that need to be met that to make the forecast need to look realistic? However you define realistic in this case. And then there's often already a solution that's out there, but may be suboptimal in some way. So it's good to know what the current approaches are and if your algorithm can improve on them or do as well or do worse. So you have some baseline for comparison. You then, if you are able to answer all these questions and move forward, you then need a data set. Most data sets consist of 3 components: metadata, that kind of data you don't explicitly use for training, but is important to keep track of, so you know like where and when example data point occurs. You have different input columns. This could be things like temperature, pressure, wind, whatever weather or population variables you have, and then you have your output, which in this case is predicting hail, but it could be any other outcome you desire. How do you get this data? There's 3 general approaches. One is go find some existing data and adapt it for your problem. You can also try to gather your own data if there isn't any existing data or it's not appropriate for what you're trying to do. And if there's no existing data available or it's too expensive to gather your own data, you may want to generate simulated data, either by, say, running a numerical model a bunch of times over different conditions, or if there's some other way to generate synthetic data for your problem, you can do that. And this can be also more of an experimentation type thing. But for more sophisticated data generation, you could use this as a full operational system. Finally, you want to pick some candidate models that make sense in terms of their like complexity relative to the problem, ability to handle the data, and like how much you understand these models already. Before we get into the machine learning part, we have to get our data ready for the machine learning portion. Often a lot of weather data comes in lots of different formats, whether it be point station data, large 3D model grids, mixtures of 2D model grids, that are on different map projections and all the kind of general data problems that one runs into, even with regular weather forecasting without any machine learning. For machine learning, one of the key things you have to do is often take these data cubes and turn it into something that looks more like an Excel spreadsheet. And this can be a very labor-intensive process to put this together. Often, once you are able to do this, it may make sense to do some kind of data scaling and standardization. Some data are kind of like exponentially distributed, like rainfall, hail size, tornado intensity, a lot of interesting weather kinds of things. The extreme stuff tends to be very rare, so you may need to either oversample the extreme somehow, do a log transformation, somehow normalize your inputs or outputs so to make the machine learning optimization process easier for certain algorithms. You also may have a lot of different inputs to your model, and you may want to be able to reduce the set of inputs to a more reasonable subset. So this may involve doing things like feature selection, where you iterate over different inputs and try to pick the ones that have the most kind of accuracy at predicting your phenomenon, have the most correlation. You can also use things like principal component analysis or empirical orthogonal functions, whatever you want to call it, and use that to take like an image and reduce it down to its major components that explain most of the variance. These are kind of common approaches here that could be helpful for both data analysis and to make the machine learning go more smoothly. Another really important component of doing good machine learning is accurately assessing how well your model is going to perform outside of the data it's been optimized on. Especially in a real-time forecasting environment, you want to know that this highly accurate machine learning model you train won't fail miserably as soon as it sees a new weather forecast. And so to do this on the machine learning end, what we do is split our data into different subsets that are used for different purposes in the model building process. The first component is having what's called the training set, which is used to optimize a model for one set of settings. So within the model, there's the actual say the weights of the model, the kind of numbers that you multiply by the inputs to get the prediction. But there's also other settings that are called hyperparameters, and these are things like the number of layers in your neural network, or how many trees in your random forest, or like how many inputs to your linear regression. All of these are settings that you can't optimize with the training data. You need a second data set, and this is called the validation set. This is not used to optimize the model directly, but it can be used to validate different configurations of the model. And this can be derived either by just picking a set of data that's not the training set, or if you have a limited size of data, you can do something called cross-validation, where you split your training data into training and validation sets multiple times, and in doing so, you can basically calculate a score that's effectively on the training examples, but because each model you trained is validated on a different subset, you can get a good estimate of validation performance. And finally, you should have what's called a test set. So this is entirely held out from the training, optimization, validation process, and this also includes like doing all the scaling and other pre-processing steps where you're selecting variables and things like that. The test set should be completely unseen by the machine learning model until the very end, and then that will give you the best estimate of how the model will do outside of its training set. The reason why we have these different sets is illustrated on the right here. There are kind of two, in terms of how much you optimize your machine learning model, you can run into three conditions. One is underfitting, where your model is not complex enough to describe the data. So seeing it like with this curve, if you use a linear regression, it's not going to fit very well. and it's going to have a high error or high bias in this case. You can also run into the overfitting regime where you have very low bias but high variance in terms of, like, if you change your input slightly, you get a very different answer. Often we assume that with Occam's razor that the simplest model but no simpler should be able to explain the fit, and thus you want to be kind of somewhere in the middle in this kind of Goldilocks zone. And having these separate data sets allow you to kind of tell, especially in a high dimensional space, where you are relative to between underfitting and overfitting. One important component for determining how to split your data is that you need to know your space and time correlations among your different data points. If they are all taken from, if you have a bunch of examples from the same day, they're going to have some relationship with each other. So it's, for weather data in particular, it is good to split your data by time and space. So you don't want to have like two storms on the same day within an hour of each other, and one is in the training set and one is in the testing set, because it's not independent. It doesn't look like what your actual forecasting workflow is. By default, in a lot of machine learning toolkits, they do a random split where you could have this happen. So you'll need to do some manual curating to make sure that this is accounted for. And this can be done by like splitting, like use 1 year for training, use a different year for testing, or taking, if it's something that changes on a daily basis or weekly basis, then you can use 1 week for training and another week for testing. So that's kind of problem dependent, and you're using your expertise on that is where it's important. Now that we've kind of gotten our data understood pretty well, we're going to talk a little bit about the actual training pipeline. So first set of examples will be under the realm of hail prediction. Central region hail is a very big threat. The Denver area has gotten some really major hailstorms. We even had one relatively recently, like in Golden, Colorado Springs, although it's been otherwise fairly quiet this year. And this work has been done with funding from NSF and NOAA JTTI with the collaborators listed below. For some refresher on how hail grows, basically you need a thunderstorm, a strong wide updraft, and you need your hail not to melt before it reaches the ground, which often depends on the temperature and moisture profile. And so this is a combination of storm and environment characteristics that we need to feed together and to make these predictions. And so like, just using one of these factors is not sufficient to get a good hail prediction. Machine learning, though, is one way to bring in all these different factors and try to come up with an optimal combination of them to predict the chance of hail. One method to do this is something called a decision tree. Decision trees are fairly simple. Machine learning models and quite interpretable. They consist of decision nodes where it has a question, like is the wind shear greater than 15 meters per second? If it is, you go down one branch. If it's not, you go down another branch. And then you keep descending the tree until you reach a leaf node, which contains your prediction, which could be a probability. It could be a just yes or no. It could also be a single value, like a regression. To grow these decision trees, we iteratively search through all of our possible inputs, as well as different splitting thresholds in these inputs, and we find the one that most reduces our prediction error when we make this split. When we do this iteratively by going down each branch and repeating the process with the data that matches these conditions, and in doing so we can build our model. What this looks like in kind of a visual context, you basically take your domain and cut it into a bunch of small boxes, and in each box we just average the data points. So it's a way of finding kind of analogs instead of just using like a distance function and saying where are the nearest points, or say what's anything that's in this box we'll consider together to make our prediction. In this example, the red areas have a higher probability of hail and the blue examples have a lower probability of hail. So we kind of get a rough, this is a fairly small decision tree, so the boxes are fairly coarse, but as you add more layers, you can refine this further and further. regular decision trees have a lot of weaknesses associated with them. They are interpretable, but they're also usually not very accurate. They're very brittle in terms of uh, you if you change a few of your data points, you might get a very different decision tree because it'll change where the optimal barrier, like splitting thresholds are. But you can take advantage of this brittleness and actually create a forest of trees or an ensemble of trees that combined with some randomization for each tree, you can actually make it, when you combine the predictions of the trees together, you can get a very accurate model. So there's two forms of randomness in this modeling system called a random forest. One is you resample your training data for each tree. This is you basically resample replacement. So some examples get repeated multiple times, others get left out, and thus you'll get a different random set of training data to grow each tree. Then you also will grow each tree with a search to a subset of the random inputs at each branch. And with this subset, this also increases the diversity of the trees and makes them a little bit less overfit to that particular set of data that is being trained on. You then average the predictions together and get a combined prediction that will be better than in the individual tree's prediction. And in doing so, you can also smooth out some of these rough barriers and kind of get a more gradations in your data. These models work they're really good at handling kind of data sets with lots of inputs because you only select a subset of the inputs in each tree for the predictions. They are pretty robust to missing data or slightly corrupted data. And they're very easy to train and optimize because the settings that work well for one problem generally work well for a lot of other problems. So you don't have to do a lot of tweaking. I like to think of random forest as sort of the second best method for every machine learning problem. And it's really good kind of out of the box. It's a good one to start with, and I've built a number of systems with it that have all performed well. One of the big areas I've worked on this is with hail prediction. So in the context of hail prediction, what we've done is we take convection allowing numerical model output, and we tested this with experimental systems as well as more operational systems like href and the HER. We look for using a image processing algorithm, we find individual storms and compile the information about their environment, so things like cape and shear and temperatures and moisture and winds at different levels. We feed that, we match that up with mesh swaths from the MRMS system. We then merge the data together and we predict whether or not hail will occur with each of these predicted hail swaths, and then what the size distribution of the hail is if hail does occur. We then can calculate other derived products like neighborhood probabilities by applying this technique to multiple ensemble members in something like an href system. And when we do that, our predictions tend to be quite good. We've seen robustness across different ensemble systems. This is a particularly good example where we capture sort of where the higher probabilities are. We capture where large hail swaths occur, and even with the lower probabilities, it still is able to capture, say, this particular area. We've also done some further calibration on the system on top of the original machine learning models. And one of the things we found recently is that in terms of Breyer skill score, we're able to get similar performance to the SPC hail outlook. Doesn't necessarily mean it's better, but we're keying in on similar things using data. This is the 12Z outlooks. We're able, using the 0Z model runs, get a similar amount of calibration. So we want this to be used as kind of additional hail guidance that's able to summarize a lot of convection allowing model output and provide the best first guess probabilities for where hail will occur, and highlight and be able to highlight different environments and support kind of all kinds of different conditions. So this isn't just optimized for, say, the Southern Plains, but you can also want it to perform well across the U.S. And it can also handle things like if it isn't like the kind of a classic setup, it can provide calibrated probabilities in across different situations. So that's an example with random forest, and I want to kind of turn to another popular machine learning method, neural networks. The basic idea behind a neural network is that we have a set of layers. So we have a set of inputs, and we have an output. This is our prediction. And in between, we have these what are called hidden layers. The hidden layers act to transform the inputs into a form that is more amenable for getting the output. So it kind of just like reshapes the data in different ways that kind of make things more visible. And it does so with these artificial neurons. And each artificial neuron essentially consists of a linear regression on the inside. It has a set of weights associated with each input. You just multiply them, sum them together. And what makes us different from just like a set of linear regressions is that we have this nonlinear activation function, and it acts as kind of a light switch. So you think of it as kind of a dimmer switch. You can turn off if the values are negative, the neuron turns off. It doesn't contribute its information to the final prediction, but if it lights up, the more it lights up, the more influence it has on the final output. So effectively, this allows the neural network to have some representation of different regimes embedded within it. So if you push your inputs in one direction, some neurons will light up and the other ones will turn off, and vice versa. So what this looks like in practice compared with a random forest is we generally get a smoother representation of the domain, and can like also kind of fit in high dimensions and do kinds of iterative optimizations and other things like that. Also has different extrapolation behavior where as you go off, it kind of assumes a linear pattern based off of the examples near whatever part of the space you're in, whereas the random forest, it takes sort of the closest example and just assumes whatever predicted value is there, it will continue to be that value even if you keep going off in one direction or another. So what I've shown so far works well for tabular data, but what if you have an image or image-like data? Often there's assumptions we can make about images, namely that we're looking for things that are occurred in like a localized area, like say a storm has some kind of spatial structure associated with it. Storm may occur in different parts of the image, and so instead of in our regular neural networks, we have weights that are associated with every input, which could be like in the case of an image, it's every pixel in the image, and so your weights can multiply quite quickly if you just have them all be independent and have a lot of different connections. So with this, we can, with a convolutional neural network, we can have these what are called convolutional filters and run them over the image. And they're basically, it's just a set of weights that are shared across the image and only focus on a small patch of the image at a given time. If you have multiple convolutional filters, you can then learn different features in the image. We also can do what's called pooling, where we can reduce the size of our image by taking the maximum in a given location and feeding that forward. Here's an example showing what this looks like on a radar image. As you go deeper into the image, we light up certain parts of the image but not others, and that allows us to predict hail probabilities. I'm going to skip ahead a little bit and give an example of how this can be used for hurricane intensity forecasting. Less of a concern for central region, but definitely a major domain area. We're focused on predicting hurricane intensity prediction. With this example, it's in the Atlantic. We trained on HWRF data from 2015 to 2017 and tested it in real time with real-time data from 2018. One of the key things we used was using time difference fields instead of the fields at a given time, and this seems to correlate better with if the hurricane is going to intensify or weaken compared with just saying what is the current intensity right now, or what is the current atmospheric conditions. So we do this with both spatial fields and with kind of summary values for different hurricane qualities or quantities. And we find that compared with HWRF, with both the random forest and the convolutional neural net, we're able to get a pretty big improvement in mean absolute error of our change in intensity, especially at longer lead times. The models get some more similar performance in the 0 to 24 hour, or at least 24 to 48 hour lead time. But at longer lead times, we're able to see a bigger advantage here. So that's very promising. We're continuing to work on improving the system. A couple of things I wanted to touch on before the end. One is that machine learning is not just, we don't just want to get a good prediction. We also want to understand why the model is predicting what it does. And so I've been working a lot on different techniques for interpreting our machine learning systems. One way to do this is with something called a partial dependence plot. With this, you can basically learn about the sensitivities of different inputs. What you do is set all the values of, say, your temperature to a single value. You feed this through your machine learning model. This is kind of a counterfactual approach. So we say, what if the temperature was 280 for all examples? How does that change our mean prediction? And we can run this over a range of temperatures, and we can see over what range do we see the biggest change in the prediction values, and that tells us where the greatest sensitivities are for our particular problem. For hurricane intensity prediction, we can see that if the maximum wind speed or the minimum sea level pressure are changing by large amounts, that's when we have large increases or decreases in intensity. We can also see the sensitivity of wind shear in this case, which is a little bit more of a complex pattern compared with wind and pressure. We can also do interpretation on deep learning models. One approach is something called a saliency map. This is where we take an image, we feed it through our trained neural network, and we compare our desired output with, say we want 100% chance of hail. We compare what the current image's prediction is with that desired label. And then we backpropagate those differences. So we run the model backwards, and we can highlight the regions in the image that will change the most to increase the probability of hail, for instance. In doing so, we can actually recover spatial structure from our neural network directly. And we can see things like different neurons will actually activate different storm types. In this case, we can get us like a supercell neuron versus a bow-echo neuron or a pulse storm neuron. And we can map those out. And this is kind of a climatological map. And we can see that the supercell neurons tend to occur preferentially in one part of the country, and the other neurons tend to occur in other parts of the country. We can look at this in terms of individual examples as well and see, given a certain input, where in the hurricane is the neural network focusing its attention as it's evolving. And so that maybe that can help forecasters with assessing how much they trust the machine learning algorithm, or maybe provide some, like, look at this area if you weren't already looking there to kind of gauge like where, like, if we're comparing between model runs, maybe we should focus on this area and see how different it is in our different ensemble members. We can also use this to create other products like highlighting storms in our real-time forecasts that are more likely to be supercells versus squall lines. So we're actively working on this project as well. And we're looking for human forecasters to help hand label some of these storms so we have a baseline of comparison with our machine learning methods. So if you're interested in this, please feel free to reach out to me afterward. Finally, I wanted to hit on a couple points on challenges in machine learning and barriers to operations. There are a lot of challenges facing machine learning. It's really popular, but when you get it to run, you run into lots of problems. So one is extrapolation. How does our model behave outside the bounds of our training data? If you're doing things within the bounds, it generally works pretty well, but outside of it, how you set up your model is very, very important and will have a big impact on what the predictions are. We also run into problems called distribution shift, but this is basically when your system changes, like when we have say a pandemic or global warming or some other or your numerical model system gets updated, the machine learning model often will fail to adapt, but people are looking at ways to try to account for this and make the transitions more smoother. There's also issues with over-optimization. If you pick one metric to optimize on, it may result in the model doing really well in that metric, but then will perform miserably on other aspects that are also really important. And how you build your data set is really important, and what assumptions are made throughout the pipeline. If they're made with data that doesn't contain certain underrepresented classes, you'll get bad performance on those classes. In the context of weather, this could be like your model does really well where there's a lot of hailstorms, but it may not do so well where hailstorms are rarer. It could also, different populations may also be impacted differently by your model, especially if they aren't represented in the training data. A couple final broader points. I know I'm kind of running low on time here, but I wanted to mention some other issues with transitioning machine learning to operations. One is that performance is not an outcome. So in addition to measuring how good our skill scores are, we also need to see, are we actually, is using machine learning in the system actually saving lives and property, resulting in better decisions, saving time in the workforce? All these really need to be tested in our testbed environments before we deploy all these machine learning systems to the wild. We also need to make sure our systems satisfy the constraints of operations that are often very different from a research environment, and a few of them are listed below. A few other barriers to machine learning. On the machine learning side, our software has gotten a lot better, but there's still a lot of changes that go on, especially with things like, say, TensorFlow or other machine learning packages that suddenly change, throw out their old API and put in a new one every 6 months. These kinds of problems make it a lot harder to maintain a system for the long run. It may be an issue in a organization like the Weather Service where software cycles tend to be a bit slower. There's also just needs for things like safety standards and model versioning and other data pipeline stuff that needs to be built. On the NOAA side, it would be good to have more robust data infrastructure, more machine learning education, and guidelines on transitioning to operations, and more communication between developers and forecasters. And to do this, I think having forecasters work with machine learning more directly could help with this process and help provide more feedback loops and cycles that can help myself as a machine learning developer and researcher build products that are more in touch with forecasters' needs. If you're interested in learning more about machine learning, there's a lot of stuff going on right now. Here's a few major events. Particular NOAA AI workshop. They're having talks every Thursday for the next few months. That tomorrow they're going to be talking about NOAA Center for AI. So it'd probably be a good one to tune into and find out what's going on with that. There's also a number of short courses and summer schools I've been involved with that I encourage you to check out. So with that, I'm happy to take some questions, and thank you for your time.